This is section 1.1, a preview of calculus. So, first of all, we need to talk a little bit about what calculus is. For a lot of people, it feels like a scary thing to come up against a course like calculus because you've heard perhaps that it's a hard course and things like that. And I guess there's some truth to that. But the thing that I've noticed after years and years of teaching this is that the biggest problem students have with calculus is not the calculus concepts themselves, but all of the things they're supposed to still remember from algebra and precalculus that have slipped their mind. And so it's those things that are difficult for a lot of students, and understanding calculus isn't really that big of a deal. I think it's a pretty easy concept to grasp. So let's just get started, and we'll see that probably if you have difficulties, it's with algebra or precalculus concepts, not the calculus ideas. Well, first of all, calculus is the mathematics of change, which is what we're going to be talking about. Velocity, which is, the rate at which you're moving is a velocity in a certain direction. Acceleration is the rate at which velocity is changing. We're going to talk about tangent lines, slopes, areas, volumes, arc lengths, and all kinds of stuff. And of course, these are things that are basic to a lot of scientists, engineers, and economists. They use calculus to model real-life situations. Now, in precalculus, I know you deal with things like velocity and acceleration, and maybe physics class as well, tangent lines, slopes, and so on. But there's a big difference between the precalculus idea and the calculus idea. Most of the time, precalculus is going to be a static thing. What is the velocity at a particular time? Or what's the velocity over an interval of time? And that's going to be very different from the dynamic nature of calculus. So let's get into this a little bit. An example. An object traveling at a constant velocity can be analyzed with precalculus mathematics, whereas to analyze the velocity of an accelerating object, you need calculus. Or the slope of a line can be analyzed with precalculus mathematics. However, to analyze the slope of a curve, you need calculus. So, again, what is calculus? Here's some more examples. The curvature of a circle is constant and can be analyzed with precalculus mathematics. To analyze the variable curvature of a general curve, you need calculus. The area of a rectangle can be analyzed with precalculus mathematics, but to analyze the area under a general curve, you need calculus. So each of these situations involves the same general strategy: the reformulation of a precalculus mathematics idea into a calculus idea through the use of a limit process. So one way to answer the question, what is calculus, is to say that calculus is a limit machine that involves three stages. The first stage is a precalculus mathematics concept, such as how do you calculate the slope of a line, or how do you find the area of a rectangle. Once you have that precalculus notion down pat, then you're ready to go to the second part of this process, which is the limit process. And then the third stage is a new calculus formulation, such as the derivative or the integral. And those are the two major branches of single variable calculus: is the derivative part and the integral part of calculus. And so we're going to start with derivatives and get to integrals later. But today we're actually going to kind of ease into those two ideas with kind of a general notion of how they work, and then we'll dig into specifics in later sections. So in the next couple of pages, there are some links between a precalculus concept and its calculus counterpart. So I'm going to read through some of them, but you can read the rest. It's not that hard. Find the value of f of x when x is c. That's nice without calculus kind of operation. Substitute c into the f of x and calculate it. But like that, the calculus part, this is differential calculus, the derivative part of calculus, we can find the limit of the function f of x as x approaches c, not when it is c. Slope of a line, delta y over delta x. The slope of a curve, dy over dx. And we'll get into all of these specifics later. The secant line to a curve, that's a line that passes through 2 points of a curve. And the tangent line to a curve. That's where the tangent line touches the curve at 1 point only. In that vicinity anyway. The average rate of change between one time and another, and the instantaneous rate of change at a particular instant in time. Curvature of a circle for precalculus, curvature of a curve for calculus. Height of a curve when x is c for precalculus, maximum height of a curve on an interval, that's calculus. Okay, so some of these things will be accomplished and looked at in Calculus 1. Other things will be in Calculus 2 or maybe even Calculus 3. So when you get into 3D things, that's pretty much Calculus 3, where we might be able to find the tangent plane to a sphere. We want to be able to find the tangent plane to a surface. That's definitely a 3D thing. That's Calculus 3. Okay, now skipping down to integral calculus. Area of a rectangle is a precalculus notion. Area under a general curve, that's using integral calculus. That's that second half of calculus. Work done by a constant force versus work done by a variable force. Center of a rectangle versus the centroid of a region. The length of a line segment versus the length of an arc. And then we get into some 3D examples. And then sum of a finite number of terms and the sum of an infinite number of terms. So we'll be doing many of these concepts in this class and then moving into Calculus 2. So at some point in time when you're in Calculus 2 or 3, you might look back at this list of things and see how many you can check off as things you know how to do. Well, let's use as an example for differential calculus as an approach to it, the tangent line problem. So first of all, to do either derivatives or integrals, we're going to have to understand what a limit is. It's very fundamental in the study of calculus. These two classic problems we're going to look at today, the tangent line problem and the area problem, should give us an idea of the way limits are used in calculus. In the tangent line problem, you're given a function f. I'll just draw some function f. And by the way, I try to make verticals look vertical and horizontals to look horizontal, but I often fail. You'll just have to assume that I meant well and messed up. So please forgive me for any of the graphs that you see that aren't quite what you want to see, not drawn as well as you'd like. So let's say we have a function y equals f of x. And I'm interested in finding the tangent line to the curve at some point on the curve called point P. And the tangent line would look something like this. Okay. And then once we know the slope of that tangent line, we'd want to find its equation. And in general, and this is going to carry you quite a bit of ways, the precalculus notion of going from some point that you're given that's on a line and taking a slope of that line, you can use what's called the point slope formula for the equation of a line and find the equation by substituting in y sub 1 and x sub 1 and m into this equation, this formula, for the equation of any line that passes through point x sub 1, y sub 1 with the slope m. It's called the point slope form. and it's extremely useful for us. You're going to be using this a whole lot. Now, there are other forms of the equation of a line, and the one I want to harp on a little bit is one I don't want you to use much because it's more complicated than necessary. Oh, got ahead of myself. This slope-intercept form is not very useful in calculus. So you might want to kind of get that one out of your head. It's not as useful as the point-slope form. So for us, don't worry about y equals mx plus b form. Point-slope form is just fine. Okay, so except for the case where the tangent line is a vertical line, which has no slope, as long as there is a numerical slope, we can use the point-slope formula. And we'll use that to find the equation of the tangent line to the curve at point P. So what we're going to do to accomplish that, I'm going to pretend like I can draw exactly what I have above. I'm drawing it a second time because the picture that I draw will get awfully cluttered if I don't split it into several versions. So please forgive me for doing this. So what I'm going to do to approximate the tangent line slope for point P, say P is right here, is I'm going to form a secant to that curve. So I'm going to pick just some random point. You know what? I think I need to make my picture a little bit different so you can see what's going on better. So pardon me for making this change. I'll do it up here as well. Because right now it looks too linear for my purposes, so I need to make it a little bit better picture. So let's make this go like this instead. Okay, so the idea would be to pick another point on the curve, either on the left or right side. I'm going to do it on the right side, although it doesn't matter. And I'm going to form a line that goes through point P and this other point wherever it happens to be. And because I know the coordinates of both of these points, I can find the slope of this secant line. So we're going to notate the slope of the secant line with m subscript sec for secant line using the slope formula. So do you remember that? So this is the part where I was saying earlier, there's lots of stuff you're supposed to know from prior courses. The slope-intercept form is one of those ideas, and the slope formula is another. The slope given 2 points is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay? And let's give these points some coordinates. Let's say that point P is at C, so this is x equals C, comma, f of C, whatever we get for y by substituting C into the function expression. And then let's call this other point Q. And what we're going to call Q is C plus delta x. So what we're going to do is we're going to move from C over a distance of delta x, change in x. And we're going to call that generically C plus delta x. And then the y value will be whatever we get when we substitute C plus delta x into the function formula. Okay, so that's point Q. So that means that our slope is, if we're thinking of point P as the first point and point Q as the second point, we'll have y sub 2, which is f of c plus delta x, that's the y coordinate of point Q, minus the y coordinate of point P, which is f of c, divided by x sub 2, which is the x coordinate of point Q, c plus delta x, minus x sub 1, the x coordinate of P is c. And if you set it up correctly this way, where P is your c comma f of c and point Q is c plus delta x comma f of c plus delta x, what's going to happen in the denominator every time is that it will simplify to be delta x, because c minus c is 0. Okay? So if you thought of a triangle that you could draw using PQ as the hypotenuse, and this horizontal piece, which is delta x long, and this part of the right triangle, which is f of c plus delta x minus f of c in length. You can see how the slope is the change in y over the change in x here. Okay, so now the idea is if this second point Q is moved from where it is right now at some generic place closer to point P, then that secant line you get, and I hope I copied figure 1.2 part B into your notes, because that's better than what I'll be able to draw. What's going to happen is, for this function and this point P, and various places where Q could be. Let's say it's kind of far away first, and there's a secant line, and then we move it closer. Say Q is now here, and there's its secant line, and we move it even closer, and here's Q pretty close to P, and there's its secant line. And as Q moves closer and closer to P, as the point Q moves in towards point P, what happens to the slope of the secant line? Well, if you look at the picture way up there where I had a tangent line drawn, let me draw that in now. Here's a tangent line. The slope of the red line is, let's say, a pretty big positive number, like 4. And then the slope of the blue one is maybe 3, and the yellow one's maybe 2, and the orange one, the slope of the tangent line is 1. So what's going on? Well, as the point Q gets closer and closer to the point P, the slope of the secant line approaches the slope of the tangent line. And that's really the basic idea behind a limit, is what's happening as something changes and gets closer and closer to something. What's the resulting value? And so to state this in a more mathematical way would be to say the limit as Q approaches P, that's an arrow, Q approaches P, of, we're taking the limit of the secant formula, as Q approaches P, it will approach the slope of the tangent line. And by the way, for a very short time, we'll deal with slopes of secant lines. And so we're always looking for the slope of the tangent line to a curve at one point. So we're going to end up calling that just plain M and dispense with writing the subscript TAN for tangent. Just want you to get used to that, because that's what we're going to do. So that's going to be what's going on. And let me say one more statement about this, which is probably a better statement than Q approaching P. What's happening to make Q approach P? Well, if you look at one thing I defined there, delta x, as point Q gets closer and closer to P, what is the size of delta x? Yes, it is getting smaller and smaller. In fact, it's approaching 0. And so that's going to be the basis of how we find the slope of the tangent line to a curve, is by finding a formula for the slope of the secant, which is this up here, and take its limit as delta x approaches 0. So here's where you're getting the first idea of how a limit takes the precalculus notion of a slope of a secant line, which we know how to do slope of a line between 2 points, and with calculus in the limiting process, we're able to find the slope of the tangent line to the curve at that point. All right, we will come back to that later and flesh that out in more detail. All right, second big example of calculus, and this is going to go to integral calculus, which we actually won't come back to until much later in the semester. We're going to be talking about differential calculus for a good part of this first semester and get to integral calculus toward the end. So let's say that we have a function y equals f of x, and we want to start at x equals a and go to x equals b, and I'm going to draw a vertical line at x equals a and a vertical line at x equals b. A couple of notions that are key to this, and this will be really brought home in calculus too, but I'm going to say it now so that you're really aware of it. F has to be a continuous function for this whole process we're talking about to work. So that's really important. And A and B must both be real numbers. And the exceptions, when they're not real numbers, will occur in calculus too. So this is really foreshadowing quite a bit. But anyway, you've got that idea. And what we're trying to find is, what is the area of the region bounded above by f of x, on the left by x equals a, on the right by x equals b, and on the bottom bounded by the x-axis. So in other words, what's the area of this region with kind of an interesting top to it? The bottom and sides are straight, linear things, but the top is curved. Okay, so that's going to be what we try to do. And so let me draw another version of that. Like I said, I sometimes draw multiple versions of it because the picture gets too crowded. And so pretend like this is exactly the same function as what I drew over there. I'm sure it's not exact, but that's okay. Not that worried about it. Okay, A and B. And what we're going to do is we're going to subdivide the region from A to B into subregions, subintervals. And let's say, for example, I do 4. So cut it in half, and then there's a fourth, and there's 3/4 of the way. And what we're going to do is pick some way of determining a point on the curve somewhere between A and the first green mark, and making a decision about letting that point represent what we want. So I know it's kind of vague sounding, but let's say that let's pick the left-hand side of the first subinterval, and that's the point that's going to give us something in this. So what I'm going to do is I'm going to allow that to be my y value that I'm using, and I'm going to draw a horizontal piece, and then a vertical down to that first green mark. And what I've created there is a rectangle. And I can find the area of that rectangle, right? So if I keep doing that, so some point between the second mark and the third mark, just pick up, and this time I'm going to make it sort of a random point like this one. And I'm going to draw a horizontal over to the verticals of the second mark and the third mark. And that's just a random point. And this time I'm going to use the right-hand side, its y value, to be the top of my rectangle. Wow, that is not straight. Sorry about that, folks. I think I can erase that line at B and make it a little bit more pleasing aesthetically. I really don't want that to look nasty. So let's pretend like I drew it well to begin with and didn't make that vertical thing look like it was such a slanted thing. Okay, there's B. And then again, just some point. I'll use the right-hand point to determine the height of my rectangle. And so the height of the rectangle is a y value on the curve. So for example, this one is f of a, tall. And if I knew what a and b were, like if it were 1 and 7, let's make it 1 and 9, that'll be easier. As an example, say this goes from 1 to 9. Well, how far is it between these two? Well, it's 8, right? And you could get that by taking the larger number minus the smaller number, right? Generically, that would be b minus a. Then, if I divide it into 4 subintervals, how large is each one of those? So, how large is this one? Well, if I divided 8 into 4 equally wide things, each one is 2 in width, right? We got that by taking 8 and dividing it by the number of subintervals. Again, we got the 8 from 9 minus 1 divided by 4 subintervals. And so generically speaking, that's b minus a. And the number of subintervals is going to be represented by n. So in this problem, n is 4, meaning we have 4 subintervals. And we're generically going to call that the width of each subinterval. That's the change in x from the left side to the right side. So that formula, delta x equals b minus a over n, that will come back into play later on in this course. Okay, anyway, so if you understand that, could you multiply a y value calculated for that point between a and the first green mark, where this one happened to be at a because I used the left-hand side, take that y value and that delta x and multiply them, and wouldn't that give you the area of that rectangle? Then if you did the same thing for the other 3 and got the areas of all 4 of them, you could then add those areas, and that would be an approximate value for the area under the curve. It's not perfectly that, but it's not too bad of an estimate. And if you look at figure 1.4, which I'm not going to try to recreate, if you have more subintervals, more rectangles, like they show 4, like I did, and then 8, the error that you're getting is smaller than with 8 than it is with 4. See, the error is anything that misses the area under the curve. So like all of this up here is error. That's too much. I went over. And this is too much. And that much is too much. Oh no, too little. I'm sorry, that piece there is too little. The rectangle is below the curve. And this amount is too much. So it's probably a little bit bigger the estimate than it's supposed to be for the actual area, but it's not too bad. But if you look at the other picture with 8, it's even better, because those places where it's too small or too big leaves a lot less between the horizontal and the curve, like this region right up here that I have shown here. That gets to be a smaller thing with more rectangles. So in general, if we increase the number of rectangles, the approximation tends to become better and better. And that's going to be a limit process. So if I could find a sum of the areas of n rectangles, that will be an approximation of the area under the curve that I'm trying to find. Then, to get to the actual area under the curve, f, from A to B. And by the way, if you see something formulated with, like area under f from A to B, what's implied there is that the area down to the x-axis and stop. So they're not going to say that every time, so I wanted you to kind of know that that's sort of an understood thing. And to make that happen, so that the sum of the areas of n rectangles actually gives me the area that I'm looking for, I'll have to take a limit of this sum of n rectangles and force n to go toward what? How many rectangles would I like it to be? I want it to be a big number. So if I force that to go towards infinitely many rectangles, we will get closer and closer to that actual area. So again, the limiting process of a precalculus formula, like sum of areas of a rectangle, will lead us to the exact area under the curve, and that will be integral calculus that allows us to do this. Okay, so that's an introduction. All of these ideas will be delved into in much more detail later. So here's the end of our first recording, and I will see you in class.